I wanted to work through an example problem involving Coulombs law and involving forces in general. In this problem, we have to imagine that we've got two blocks on a horizontal frictionless table. The two blocks are connected by a spring with a spring constant K. And initially, those two blocks and the spring between the two blocks is unstretched. And then we're going to add some charge Q onto each of the two blocks. That charge will repel the two blocks and the spring will stretch. And we're told that without the charge, the unstretched spring had a length of 0.4 meters, and with the charge, the stretched spring has a length of 0.5 meters. And from that information, knowing the length of the unstretched spring, the stretched spring, and the spring constant of the spring, we're going to figure out how much charge was added to each of the blocks. I got a little sketch here that I started. Here's the spring in the center. The spring constant, we're told, is 100 newtons per meter. So that characterizes the strength of the spring. And then here are the two blocks. I'm picturing here the case when the charge has been added to the two blocks. The initial length of the spring before the charge was added to the two blocks, I'm just going to call that L. That's 0.4 meters. And then the final length of the spring is 0.5 meters. And I'm going to call that L prime. And so this is the information we're told. And we got to figure out Q. We've got to figure out the charge on each of the two blocks. So this is really a problem of understanding the equilibrium of the various forces in this problem that happens when you place the charge on the blocks and the spring stretches. So if I imagine the block, say, on the right-hand side, that block is being repelled through the electrical interaction, through the electrical force from the other block. And so there's a electrical force on that block. I'll just call it Fe. And then that block is also experiencing a spring force due to the stretched spring. And I picture that force, it's to the left, and that's, I'm going to call Fs. And so those are the forces on the right-hand block. The same set of forces are on the left-hand block, actually. I could picture those so that there's a electrical force due to the repulsion of the two charges, Fe, that in this case is acting towards, and then there's a spring force due to the stretched spring towards the right, Fs. And when we solve this problem, we could be thinking about either the block on the left or either the block on the right. I'm going to imagine the block on the right, say. So that block's in equilibrium. That block's at rest and staying at rest. That means that the spring force and the electrical force are in equilibrium. They are equal in size to one another. They're opposite in direction to one another. And so my starting point in the calculation is really that the magnitude of the spring force is equal to the magnitude of the electrical force. I'm not going to worry about directions here, whether they're to the left or to the right. I'm just going to worry about the fact that their magnitudes must be equal. That's enough to solve this problem. I can then fill in, because I understand spring forces and now I understand electric forces, I can fill in formulas for the spring force and the electric force in terms of, for the spring force, how much the spring got stretched, for the electrical force, the distance, separation between the two repelling charges. So let me just fill that in. And so here's my two equations on the left and right for the working of the spring force and the working mechanism of the electric force. So the magnitude of the spring force is the product of the spring constant K and the amount we stretch the spring. And the amount we stretch the spring is not L prime or it's not L, it's the change, it's the difference between L prime and L. So I fed that in. And then over here on the right-hand side, this is how the electric force works. So it's the Coulomb constant. So this is Ke, not the spring constant. K was the spring constant. This is Ke, the Coulomb constant, times the charge, product of the charges, which is going to be Q squared in this case, because they're the same charges, divided by the square of the separation between the two charges. And that's the final separation between the blocks. And so if you look at this little equation, right, it's an equation that contains the unknown that we're interested in. That's Q, the amount of charge on each block. And all the other quantities in the equation are known to us. We know the spring constant, we know the Coulomb constant, we know the final separation, the initial separation of the two blocks. And so I can just rearrange this equation for Q. Let me go ahead and do that. So in the numerator here, I've got the spring constant. I've got the amount that I stretch the spring. And I got the square of the final separation between the two blocks. And then in the denominator here, I've got the Coulomb constant, Ke. And so that's my equation for the amount of charge on each block. And I can just fill in the numbers to that equation. See if I can do that. So the spring constant is 100 newtons per meter. The amount we stretch the spring is 0.1 meters. The final distance between the two blocks, that's 0.5 meters. Let's square that. And then in the denominator here, we got the Coulomb constant. So that's 9 times 10 to the 9. And the units for that are newtons, meter squared, divided by Coulomb squared. If you look at all the units in this equation here, what you see is a lot of cancellation. The newtons in the numerator here cancel with the newtons in the denominator here. The meters in the numerator here, so in the numerator here, there's a meter squared, another meters here, but an inverse meters here. So there's meters squared in the numerator. They cancel with the meter squared in the denominator. And all we're left with is the units of coulombs. And that's the units of charge. So that makes a lot of sense. Actually, here we got the square root of 1 over Coulomb squared, which is the square root of Coulomb squared, which is a Coulomb. And so that's the correct units. And finally, if I calculate the number, I multiplied all these quantities out, I got 16.7 microcoulombs, 16.7 times 10 to the minus 6 coulombs. And that's the answer to the problem. So that problem was a illustration or an example of working with Coulomb's law and our understanding of the mechanism, the working of Coulomb's law, and also more generally in working with forces. Here we have the spring force and the electric force, and working with forces in equilibrium.